the sacrament of the humanist religion. Let's see here. I'm unplugging my mic. Better make sure I didn't just unplug it. Nope, we're good. So the verse that you guys have chose for me today, do not lie to one another, seeing that you have put off the old self with its practices and have put on the new self, which is being renewed in knowledge after the image of its creator. Colossians 3, 9 and 10, English Standard Version. Very good. I'll begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for the students. Just ask that you be glorified in what we do. Help us just all to understand a little bit more about manifolds today, and specifically cotangent vectors and pullbacks and all these things. Lord, in your name I pray, Lord Jesus. Amen. Okay, so let's see here. Last time we started down the path of understanding what covectors were, right? And so we defined dual vectors. We basically talked about the dual to the tangent space is the cotangent space, and you got one of those at each point in the manifold, right? So so let's talk about cotangent space, cotangent vectors, etc. So we are in chapter 11 of John Lee's book. Okay, so TP, TPM star is basically alpha that goes from TPM to R, such that alpha linear. And we discussed last time that if we're at if we have a coordinate chart, then a basis for this is these guys. So in particular, dxi of partial j is partial xi of partial xj, which is equal to Kronecker delta ij, which is the necessary condition for the differentials to be the dual basis to the usual coordinate basis. And so we had that. Then we talked about the fact that there is also a double dual, and I'm not going to talk more about that at the moment, but we'll come back to that double dual idea as we go on. And then we also talked about the cotangent bundle, right, which was, I forget the notation. Maybe it was this. The disjoint union, right, of the cotangent spaces, right? And I mentioned that if you want, you can build an adapted coordinate chart, like phi tilde of p comma alpha, straight up. What you got is x of p, comma, alpha of, alpha of partial 1 at the point P, alpha of partial 2 at the point P, alpha of partial n at the point P. I'm using, at the moment, a more abbreviated notation, namely that partial I at the point P is a notation that is a shorthand for this. That is a notation which has served me well. So there you go. Now, we could talk about alpha, and I really maybe, I don't know. See, let me just be annoying and dress things up with P. Like, this is the thing. It's like, you start doing stuff like this. Do 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 do. Do you really need, how many P's do you need? I don't know. You could do that if you want. Just emphasize it's at a point, all right? In contrast, I could talk about alpha an element of the covector fields on M, it means we can write alpha as equal to something like a sum I equals 1 to n, alpha acting on partial xi times dxi. So this, of course, we could also write as just alpha sub I. It would be a mapping from U to the reals. Here I'm assuming that Ux is an element of the atlas of M, right? So there the component functions are smooth functions, yeah? And this is a covector field, okay? And I talked to you guys a little bit about how coordinate change worked last time, and I argued that the adapted coordinate chart could easily be shown to be smooth because basically if you compare two adapted coordinate charts built from two different choices of coordinate charts for the manifold, the transition functions are smooth because, well, transition functions of regular coordinate charts are smooth, and also, the other thing that you end up with is just like partial derivative of the coordinate with respect to the other coordinate system, which is again smooth. To judge the smoothness of a covector field, there's like a bunch of different ways to look at it. The one way is it's smooth if for any smooth vector field, when you let it act on a smooth vector field, you get a smooth function, all right? Another equivalent condition would be the smoothness of the coordinate charts. The component functions. If these are all smooth, that makes alpha smooth. There's, I think, two other ways the book had to look at it, but those are the two I often think about. This here is actually a C infinity module. In particular, if you have alpha is in a covector field, and f is a smooth function on the manifold, then f alpha is also a covector field. And the value of f alpha at the point P is simply defined by f of P, alpha of P. Alpha sub P, maybe you'd write. So it is a C infinity module. You can also talk about frames, all right? Dual frames. So if you have E1 En frame on, let's say, Tm, right? Then you can talk about epsilon upper 1, epsilon upper n coframe on T star m. And if the coframe is dual to the frame, you need the following condition. You need that epsilon upper I acting on E sub lower j is equal to Kronecker delta ij. Now, John Lee is more, I think he maybe puts an upper I and a lower j or something like that. I don't care. Sorry. I should care. I was raised by physicists, so I do have certain physical prejudices in that regard, but yeah, I don't know, I can't care. But so an example of a frame and a coframe would be the coordinate frame, like partial x1, partial xn. That gives you a coordinate frame that's defined on the chart domain. The coframe to that would just be the set of the differentials, dx1, dx2, dxn. An obvious and somewhat technical question to ask is, if you're given a frame on Tm, maybe not necessarily a coordinate frame, is it possible to change coordinates such that your given frame becomes a coordinate frame? That's an interesting question to ask. We've seen in terms of previous chapters that would force, that only be possible if the commutator with the Lie bracket between any of the two of the members of the frame has to be 0, right? Because coordinate partials commute. So if you could somehow change coordinates such that your frame became a coordinate derivation, it would have to have a Lie bracket of 0. But the Lie bracket is coordinate invariant. So if the Lie bracket 0 and 1, it'd be 0. So yeah, so there's that. Now, this led us, not necessarily in this order, to define the differential of a function. So this was a big deal. If we've got a function, right, from, let's say, u, a subset of m, to the reals, then d f p of v is simply equal to v. I like to write brackets f. He just writes vf. But I like to write bracket f, partly because of differential equations and my typical use of like operator notation. It's the operator v acting on the function f to give you a new function. Okay, fine. At the point p, it gives you a value p. But if you think about the assignment, p maps to dfp, like this. This gives you a covector field. Say df, which would be an element of the covector fields on M. Now you guys notice that this is somewhat at odds with our notation for push forward, right? Because push forward, how did it work? We feed it a vector and out pops a vector, right? Here we're feeding dfp a vector and out popped a number, a scalar, right? So this is an element of our, or if we let p vary, if you let p vary, out pops a function, right? So that's a different use of the differential notation than before. As I mentioned last time, it amounts to making the identification that the tangent space to the reals at a point, let's say t naught, is just identified with R itself. Basically, what's going on here is we're saying ddt at t naught is identified with just the number 1. So you do need to keep that in mind in order to be completely consistent with the formalisms. There's an identification which is being made, but you know what? The good news is it's not just John Lee doing it, it's everybody doing it. But most people don't say it's an identification, they just say, well, I don't know what they say. But he's pretty careful to talk about things in terms of pointing out when we're making an identification, right? Which is to say we're using an isomorphism between two different objects to write, rather than writing the isomorphism, right? Technically speaking, you should always have like some kind of mapping that goes between these two things, and every time you use this, that mapping should be pure. It would just get very tiresome to write that, so instead we just say equals, which is a lie, but it's useful. Oh, I don't know. So I think at this point I've just reviewed, then I talked about proposition 11.20, and so we're on page 282. We're not to 300 yet. I just bought a copy of Dune. It's only like $5.50 on Amazon Prime right now.
What's $5.50?
Dune. Yeah, like ultra high def.
I'm getting paid to say it.
Not as far as I know. Save my son the trouble of pirating it, you know. So it's good.
It's less effort.
What?
Yeah.
It's pretty much the only movie I want to see in the theater, like, I don't know, this decade maybe? It may be the only movie I want to see in the theater like this decade, honestly. Equalizer 3 feels like a watch-at-home movie. It doesn't feel like I need to go to the theater movie. I haven't seen that yet, but I do enjoy the scripted violence of Denzel Washington. Like, it's just something very wrong about such a gentle man being so very violent, you know? Yeah. He is. I see here. So anyway, proposition 11.20 gives us the properties of the differential, which are awesome. We will use those. And proposition 11.22 this says that if f is a smooth R-valued function, on manifold M with or without boundary, then df equals to 0 if and only if f is constant on each connected component of M. I added the language connected component. I think he just says component, but since you guys, are new to this, I'll just say connected component. So this is the analog of, like in calculus 1, we have that theorem. If the derivative of a function is constant on a connected domain, if the derivative of a function is 0 on a connected domain, the function's constant. This is saying that generalizes to a manifold. Let's look at the proof. I think it's interesting. So he says, suffices to assume that M is connected and to show that df equals 0 if and only if f is constant. One direction's immediate, right? So the converse direction is stupidly obvious, right? So if f, if f of p is equal to c for all p and m, then df is equal to 0. Okay, great. Yeah. And that, you can see that by the definition, right? If you put a constant function and let a vector field act on a constant function, we proved that was 0 a long time ago. If it's 0 for every constant function, then df is equal to 0. That's the logic. Do you guys get it? Like, I put a constant here, it's 0, because the differential, a partial derivative acting on, well, a derivation acting on a constant we proved was 0. We did this. Like in class maybe, like 1 times 1 is equal to 1. Product rule, v of 1 times 1 plus 1 times v of 1 equals to v of 1. Therefore, v of 1 was 0. And from that, the linearity gave us that v of c was 0. So, which is actually how I proved the derivative of a constant was 0 in calculus 1 this semester. You don't always think about this class influencing other classes, but it can happen. I didn't tell them. Yeah, the secret has to stay here. The other direction. You've done something wrong in your calculus 1 class when you tell your brother who's a mathematician what you did, and he goes, "Oh, that's a nice way to do that." Like, what if he says that? It's not good. Whatever I just did. Let's see here, because that's the abstract algebraic way of proving the derivative of 0. It's completely divorced from limit. That's just part of the formal calculus. All right, so forward direction. It says conversely, suppose df is equal to 0. Sorry, I gotta keep it going here. I know I still need to vote today. It'd be a shame if Donald Trump couldn't somehow make it eke through this primary here. I don't know. df equals 0. Oh no. Well, of course, I'm voting for Nikki. Let's see here. Where was I? So df equal to 0. Has he lost a primary? How could he? P, B, and M. He's a practically religious figure with about 40% of the Republican base. So.
That's true. I thought he had
and there's nothing like building a person up than to unjustly, like the lawfare against him has made him even bigger than he would have been otherwise. I don't know. We'll see what happens. But so let's see here. So he says, let this set be Q and M such that f of Q equals to f of P. All right. So it's the coincidence set of P. It's the set of all points in the manifold where f of P is equal to f of Q. If we can show that this set is the whole manifold, we are done. All right, so he says if Q is any point in this set here, C, the coincidence set, let U be smooth coordinate ball or half ball if Q is an element of the boundary of M, right? Centered at Q. Great. Then what? He says from 1111 we see that partial f partial xi equals to 0, identically equal to 0, and u for I. All right, so let's see here. Let me draw a picture. Here's M. Yep.
How do we know that the set's non-empty besides P?
Well, that's, I mean, we know P's in there.
I got you.
So, well, just a second here. So, Oh, you've bothered me with this question.
Are we assuming that it's not injective? Because P is that.
Well, I guess to start with, all we know for sure is that there's P in there. But if Q is an arbitrary point, but we want to do it is not empty because P is in there. That's all I know for sure at the moment. But if we, if we take this as a point Q, right, and then we take an open ball or an open half ball around Q, yeah, then so like df is equal to the sum over I of partial f partial xi dxi.
Well, yeah, but we're assuming that.
So that's the case, and so to say that that's a coordinate ball means that it actually goes down here to a honest to goodness, ball. Right? And the thing is, you've got, since this is identically equal to 0, that means partial f partial xi is equal to 0, right? Which means that like the partial ui of f composed with x inverse, I think it is equal to 0. So x inverse goes from the Euclidean space up to the manifold, then back down to the reals again. So that's just a function on Rn. So if we have a function from Rn to R, which has all of its partial derivative 0, then using calculus 3 or calculus n we have that f composed with x inverse is equal to a constant. But now all of a sudden, we don't just have p in the set. See, because if you track back, then f of u has to be equal to p. But on the flip side of things, q was an arbitrary point in this coincidence set. And we've just showed that there's an open ball or open half ball around that point, which is to say we've proved that C is an open set. All right? But on the other hand, C is also equal to the inverse image of this, isn't it? But F is assumed to be continuous, therefore C is a closed set. C is both closed and open. If M is connected, it must be that it's all of M. And then if M is not connected, you simply repeat this argument on each connected component. And so doing, we have the proposition. Good questions, guys. And then he's got a great couple paragraphs here talking about how to think about how to visualize DF. You know, how to understand it. It's the best approximation to the change in the function. Let me move on here. So proposition 11.23, here we have a smooth curve from an interval, so that would make that a subset of the reals, to M, smooth curve. And if we have f from M to R smooth function, then the derivative of the composite, f composed with gamma prime of t, is simply equal to d f at gamma of t times gamma prime of t. And I feel like I may have even done this before. Like, I feel like we may have come across this formula before as it appears in like our discussion of the equivalent viewpoints of the tangent space. I think this is essentially how I defined. Is this not how I defined the differential acting on the equivalence class of curves? I said the differential acting on the equivalence class of curves is the equivalence class of curves that is the function composed with the curve. Like, this was my definition of the differential on the equivalence class. But, you know, I may have strayed from Lee there, so that this may be the first time it appears in Lee. I don't remember, honestly. Okay, so let's prove this. Can I erase the previous?
Yeah.
Okay, cool. All right, so here we go. Here is the proof. I'll copy it down, and we'll digest it together here. So we've got df gamma of t naught acting on gamma prime of t naught. That, by definition, is gamma prime of t naught. That's a derivation acting on f, right? Remember if we have, well, that's just this definition, right? Here, this is the v of the definition, right? Then we trade this for a d gamma t naught acting on d dt at t naught acting on f. So that was actually our definition of gamma prime from back in the day. I don't know if you remember or not. All right. And then we're like, well, that is nothing more than d dt at t naught acting on f composed with gamma. He says that's the definition of d gamma. Okay. And then that is precisely f composed with gamma prime of t naught. And there it is. At this point, he confesses on the duplicitous use of the differential notation. And on page 284, he confesses to the, the identification of ddt with being 1. All right. Great. Let us go on. So I think we won't need this theorem anymore. So I'm going to, anyway, that one's easy to remember, isn't it? So there are two things in terms of like calculational techniques in manifold theory that I think are really new and interesting. And once you understand these, if you really, really understand these, you've understood a lot of manifold theory, actually. The one is the push forward, which you guys have already started to kind of fuss with. The other is the pullback, and that's what we're talking about right now. So this is pullbacks of covector fields. And I guess technically speaking, you could understand this in terms of the dual of the linear map that was talked about at the start of the chapter, but I think rather than teach you something you don't know with something else you don't know, let's just focus on what we're trying to learn. So here we have, excuse me, f going from m to n smooth map between manifolds with or without boundary. Let P be an element of M, arbitrary point. Then, as we know, the differential of F at P does what? It goes a mapping from TPM to TF of P n, right? And this yields, here's finally the thing we're defining, DFP dual, pull back if you like, mapping from the dual space to n at f of p to the dual space at p of m. Notice it goes the other way. So he says this is called the pointwise pullback or the cotangent map of f. Pointwise pull, that's a mouthful. Pointwise pullback or cotangent map of f. Unraveling definitions, he says, we see that DFP is characterized how? So how does this work? So rather than just copying it from the board or, copying it from the book, I'm going to let you guys tell me what I have to write here. And this is going to be for omega in the dual space, the cotangent space that is, at f of p to n, and for v in the tangent space at p to m. So you guys think through this. What logically must I write down here? What can I do? Like, what can I do with DFP? What can that do for me? DFP can do what? Right? So the push forward of the vector v under f like this, dfp, I take my vector at m, my tangent vector to m, and I get a corresponding tangent vector to n, right? So if one of my inputs is a v, I can convert that to a tangent vector on n by taking the differential of f at p, letting it act on v, right? Now that is a tangent vector to n at f of p, which is exactly what this thing eats for breakfast, right? Like, this eats tangent vectors based at f of p at n. So I must put the omega out here. That's it. That's the definition of the pullback. It is inescapable. If you just think about the logic of the way the symbols have to be combined, it's what you have to write. So there it is. Of course, this leads you to the question is, but what is it? Right? Like, what does this amount to, right? And, okay, so if I had been a better teacher this semester, I would have convinced you that the push forward, in some sense, is a tool that we can use to change a derivation from one coordinate system to another. For example, if you look at the push forward of, partial x, if you push it forward into another, at the same point, but push it forward in terms of the polar coordinates, what you'll find is partial x expressed in terms of derivatives with respect to r and theta. So there's a way of understanding the push forward in terms of just coordinate change. Same thing here. It turns out that we can understand the pullback is really just a way of rigorizing substitution, is what it ends up meaning after a bit here. It's more than that, though, because it doesn't just have to be, like the thing I was just talking about, substitution, coordinate change, really only makes sense. We're talking about a mapping from one manifold to the manifold again. But the concept of push forward and pullback is more general than that, because the start and the end doesn't have to be the same space. Like, we can be talking about transporting calculus objects from one space to another space, and they don't have to be the same space. So it's more than just the coordinate change idea, but the coordinate change idea is the thing you've already seen in calculus 3 for sure. Now he says, as we discussed vector fields, we made a point of noting that push forwards of vector fields don't always give you vector fields, right? Because we have that problem that if we don't have an injective map, if we have two different points mapped to the same point in the range, then we could end up pushing forward two different vectors to that one point, which wouldn't be a vector field, right? However, we know there are some special workarounds. For example, as he mentions, if we have a Lie group homomorphism, the push forward is legit. The push forward of a vector field is a vector field with respect to a Lie group homomorphism was one thing we had. And also, if we have a diffeomorphism, the push forward of a vector field is a vector field again, right? But as he says here, the surprising thing about covectors is that covector fields always pull back to covector fields. And here's how we define that. The pullback under F of a covector field omega at the point P is just defined to be df pullback P, the pointwise pullback of omega at f of P. So in particular, the way that works is the pullback of a covector field omega at the point P, when it acts on a vector v, we just get omega of f of v. I'll get out of the way here a second. Acting on df p of v. So here, omega is an element of the covector fields on n. So the pullback of a covector field is a covector field. And the interesting thing, again, is that Even if f is not 1-to-1, nothing happens. This is just things in the other direction work better, you know? It's kind of like continuous maps, right? The inverse image of an open set is open for a continuous map, right? Essentially, that's the definition. How about the forward image of an open set in topology? Not for every continuous map, right? Only for special ones do you have that openness of the map. So, you know, when we're talking about functions, things going one way and things going another way, they don't always work out the same, do they? Now, it turns out, as he mentions, that when you study this in terms of like category theory, this is a contravariant functor, which is annoying because everything else here is like covariant. So the language of covariance goes back to its origin story in physics, where things with lower indices are covariant vectors. Things with upper indices are contravariant vectors. The usage of the term covariant and contravariant as it applies to category theory is a different usage. They just, you know, just so happen to work out this way. Now, so proposition 11.25, here we have f, again a smooth map, and here we have the pullback of u times omega is equal to u composed with f times the pullback of omega. And here we have f a smooth map as usual. U is a smooth mapping on n, and omega is a covector field on n. By the way, he also mentions that you can define rough covector fields, meaning that you know, it may or may not be smooth in principle, and then he has theorems about proving rough covector fields are smooth by looking at their basically, like I was already telling you guys about, like if the components to the rough vector field are smooth, then the covector field is smooth, so forth. Now, and it says if u is smooth. Well, I said it was smooth. Oh, oops. I guess I haven't copied this proposition correctly. Oh, he just says u is a continuous real valued function on n. So to fix that, let me just say C0. There we go. Now it's continuous. All right. If u is smooth, then you have f pullback of du is equal to d of u composed with f. All right. So let's look at the proof of this thing. The proofs in this section are all, so many of them are wonderful because they're calculations, and they give you a window into how you should understand these things. And so these proofs are worthwhile. And they also help you to kind of, I've always found the proofs in manifold theory are helpful to understand the notation, if nothing else. I mean, so much of it is just that. So here we go. So f pullback u omega at the point P. All right, what's that going to be? That by definition is d, the pullback map of the cotangent map of f acting on u omega at f of p. Now that's that C infinity module stuff, right? So what do we mean u omega f of p? Well, that means u of f of p times omega f sub p, right? In other words, this function times that covector field pointwise is simply defined by plug the point into the function and multiply it by the covector field at that point. And then, because the differential is homogeneous, you can pull this guy out there. So you got u of f of p times d pf pullback of omega f of p, which is exactly u composed with f times f pullback omega, all at the point P. I'm skipping a step, but I think the step is obvious. So there you go. That's the first thing. The second thing, I'll do in the middle in red once I get my marker. Oh, Preston, I was going to tell you, maybe analysis 2 is going to go next semester. I think I might like do halvesies with Professor Schmidt. And he said something like he might do measure theory and some stuff on Fourier analysis and things like that he's interested in once he has a heart to talk about. And then I'll do other stuff. And we'll just kind of go halves. So we're not planning it together. It's like he gets 500 points in the course, I get 500 points in the course. It's a 3-hour course. We'll find a time to meet. We probably won't be both there at the same time. That's a rough sketch of what we're thinking about. So anyway.
Could I do that instead of one of my electives?
I think so, yeah. I would hope so. Let's see here. It depends on what you mean. But depends on what kind of electives we're talking about. Ooh, that's more controversial. All right, so pull back under f of du acting on v. So now we're working on this part. So to understand an identity like this, usually feed it a vector, so you can understand what where the vector goes. If it's true for all vectors, then the identity is true, right? Okay, so what's next? This is equal to d, the cotangent vector here, df star p acting on du f of p acting on v. All right. So that's just the definition. That's literally the definition. Then what next? Then we use the definition of df star. This becomes du f of p acting on df p pushing forward v, I believe. But that so now we're going to, it's easy to get lost in things, but like at this point, what we're doing is we're using the definition that I wrote at the start of class over here with dfv is vf, all right? But the f is this. This is the f, and this is the v. So that becomes dfpv acting on u. Which then becomes v acting on u composed with f. Which then is exactly the differential of u composed with f acting on v, p acting on v. But this holds for all v, therefore that's true. Let's take a second to take stock in what this is saying. This is saying that when you're pulling back a function times a covector field, right? You're pulling back a function times a covector field. The way it works is you pull back the vector field and you simply take the function and compose it with the function you're pulling back. So some people would say something like this: f pullback u is equal to u composed with f. It's like this, like the pullback of the function is a new function formed by composition. All right? This is part of a larger story which is only completely told in chapter 14, where he starts talking about differential forms. All right? We'll learn that differential forms in the pullback play together particularly nicely, and this is one of the base cases. But what that really says is just you plug the map into the function and you pull back the vector field. And this is something equally beautiful. It says that if you've got the differential of a function and you pull it back, it's the same as if you first pulled back the function and then differentiated. You see, in terms of this notation down here, notice that this becomes d of f pullback u, right? It's like you can differentiate before or after the pullback. That's how to think about this. Proposition 11.26. I'm not going to write this one. I'm just going to talk about it. Basically, it says that the pullback, if you have a smooth map and you have a covector field on n, then the pullback of the covector field is, well, the pullback of a continuous vector field is a continuous covector field, I believe is what he's saying. And the pullback of a smooth vector field is a smooth vector field. So pullback preserves either continuity or smoothness of the covector field. And the proof he gives on page 286 is basically just like look at it in coordinates and say, okay, it works. So it's not a hard proof, yeah. Ah, yes, finally, a calculation. Ooh. Well, that definition I just erased is one of the ones that you really need to like memorize that and know it. I remember as a student in this course, it was one of my main, once I really was able to use that coherently, it is so much of what put things together. All right. So let's actually look at a calculation. So here we have, and listen, for all the abstraction here, the actual way you calculate these things, it's very simple. So example, I guess it's example 1 for us. We have f from R3 to R2, and it's given as follows: f of x, y, z is equal to x squared y, and then y sine z. All right? And so basically we're going to say, well, that's u and v. So what's going on here, and I like to use the notation personally. I like to sometimes put x, y, z here just to announce, hey, I'm using variables x, y, z there. And I like to put u and v here just to say, hey, I'm using u, v on that copy of R2. Just tells me, it helps me understand what's the meaning of x, y, z and u and v, you know? And so we're going to look at the covector field. I'm following John Lee because, you know, why not? So v du. I'll tell you why not, because I don't have another 10 hours to develop my own notes. But there it is. This is a particular element of, that's a covector field on R2. And I'm not going to draw the UV. UV is just bookkeeping. It doesn't have to be there every time. You get it? So what's the pullback of omega? All right. And so here we go. Following the proposition we just proved, we do what? How's it go? I can't forget. I'm a dummy. Yeah, U composed with F. U composed with F. U composed with F. And then F pullback dV, right? Plus what? Plus V composed with F. F pullback du, right? But how does that actually calculate? Well, what's U composed with F? Well, U composed with F is just x squared y. And this is the same as the differential of the pullback of V, right? Well, anyway, getting to the point here, what does this work out to? I'm going to write this step down here just for a second. Fine. This notation may not be used by Lee at this point. I, in my heart, believe he will be using it by chapter 14. I may be a little bit jumping the gun on that notation, but I like it. And this is exactly the meaning of that. The differential of y sine z plus y sine z, differential of x squared y. But how do you take differential? Well, that's that proposition I got to at the end of last class. But it's also what you already learned in Calculus 3. So you're like, I haven't had Calculus 3 yet, at which point I will tell you, get out. See here, dy plus cosine z, oh man, cosine z y dz plus y sine z, 2x dx, good grief, 2xy dx plus x squared dy, which of course you can simplify if you like, x squared y times the sine of z plus 2x y squared sine of z dx. Oh man, what the what? That's not good. Sorry. I've done worse things. All right, so you've got yourself I'm just bookkeeping now. 2x y squared sine z dx plus x squared y sine z. Here I've got an x squared y sine z. I think I can just double it up. dy plus x squared y. I'm too close to this. X squared y squared cosine z dz. And if I've made a mistake here, it's not altogether surprising, but you get the idea, I hope. Woohoo! All right, I got it. All right, so great. Example 2. Yeah. Let's do another. So you can understand why I'd like to get to this topic before your test? Yes? These make nice test questions. They're not, you know. And believe it or not, you can actually start feeling like you're doing something. Believe it or not. We can also talk about x, y equal to r cos theta, r sine theta is his notation for this. I think to be fussy, we're doing the identity as a mapping from R2 to R2, but the deal is he's giving r theta here and xy there, like that. And